Welcome to qnawire.
In this question, we begin by calculating the acceleration of this box for then calculating how far it slides up before coming to rest. To calculate the acceleration, we have to use Newton's second law. For that, I will choose the following reference frame. My y-axis will be this axis, making 90 degrees with the slope, and my x-axis will be parallel to the slope, pointing to the direction of movement. Then, using this reference frame, we apply Newton's second law. The x-axis, it tells us the following. The net force in that direction is equals to the mass of the box times its acceleration in the x direction. And we are trying to calculate precisely its acceleration in the x direction. Then, notice that the net force in that direction is composed by two forces, the frictional force that points to the negative direction and the x component of the weight force, which also points to the negative x direction. The components of the weight force are as follows. This is the y component of the weight force and this is the x component of the weight force. Then, Newton's second law tells us that minus frictional force minus weight force component x is equals to the mass times the acceleration of the box. Then the acceleration is given by minus the frictional force plus the weight force component x divided by the mass of the box. But the frictional force in question is the kinetic frictional force, which is given by the kinetic frictional coefficient times the normal force. So we can write it as acceleration being equals to minus mu k times the normal force plus weight force component x divided by the mass. Now we have to calculate what is the x component of the weight force. For that, we can use this triangle. So this triangle is like this. This is the hypotenuse. We have one side, we have the other side. Here we have the 90-degree angle. The hypotenuse is the magnitude of the weight force. This is the y component and this is the x component. Let us use this angle as theta. Then, by calculating the sine of theta, we can determine what is the relation between the x component and the magnitude of the weight force. Because the sine of theta is given by the opposite side, wx, divided by the hypotenuse. Then, wx is equals to w times the sine of theta. Then, the acceleration is given by minus mu k times the normal force plus w times the sine of theta divided by the mass of the box. And then remember that the weight force is given by the mass of the box times the acceleration of gravity. So we get an expression for the acceleration that is as follows. Kinetic frictional coefficient times the normal force plus m times g times the sine of theta divided by the mass of the box. And now we have to calculate what is the normal force. For that, we have to apply Newton's second law in the y direction. Actually, we don't need to do so because it's very easy to see that the normal force is being exactly compensated by the y component of the weight force. But in any case, being more rigorous, we can use Newton's second law, which tells us the following. The net force in the y direction is equal to the mass of the box times its acceleration in the y direction. The box is only moving in the x direction, so its velocity in the y direction is equal to 0, and this velocity is not going to change. Therefore, the acceleration is equal to 0. Then, the net force in the y direction is equal to 0, but the net force in the y direction is composed by two forces, the net force, which points to the positive direction, and the y component of the weight force, which points to the negative direction. So the normal minus the weight component y is equal to 0. Then, as I said, the normal force is equal to the y component of the weight force. And then we can use this triangle again to calculate the relation between the y component of the weight force and the magnitude of the weight force. We use the cosine for that. because the cosine of theta is given by the adjacent side, wy, divided by the hypotenuse, w. Then, the weight force y component is given by the weight times the cosine of theta, which means that the normal force is equals to the weight cosine of theta. Then, we can go back to the expression for the acceleration and substitute the normal force by this expression to get that the acceleration in the x direction is given by minus mu k times the weight, which is m times g, times the cosine of theta, plus mg times the sine of theta, and this whole expression is divided by the mass of the box. Notice that there is a common factor of m in the numerator and a factor of m in the denominator, so you can simplify it, and then we get a final expression for the acceleration in the x direction. It's given by minus mu k times cosine of theta plus sine of theta, and this whole thing is multiplied by the acceleration of gravity. So this is the expression for the acceleration in the x direction. Now, before evaluating this expression, let me organize my board. Okay, now we are in condition of evaluating the acceleration. It's given by minus 0.180 times the cosine of theta. But what is theta? Theta is this angle here inside this triangle. So this is theta. But what is the value of theta? It's not difficult to see that theta is equals to 15 degrees. If you have a hard time to see that, just look at what I'm doing. We can extend the weight force down here so that we form a rectangle that has a 90 degrees angle inside it. Then 15 degrees plus x should add up to 90 degrees. It means that this angle up here is an angle of 90 minus 15 degrees, so it's an angle of 75 degrees. On the other hand, the angle between the slope and the y component of the weight force is also an angle of 90 degrees. Therefore, 75 plus theta must be 90. Then theta is equals to 15 degrees, as I said. So now, going back to the evaluation, we have the cosine of 15 plus the sine of 15, and this is multiplied by 9.8. In case you forgot, the acceleration of gravity near the surface of the Earth is approximately 9.8 meters per second squared. And then this results in an acceleration of approximately minus 4.240 meters per second squared. So this is the acceleration of the box in the x direction. Now we are able to evaluate how far the box travels before coming to rest. We have Torricelli's equation, which tells us that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. The final velocity when the box comes to rest is 0. The initial velocity of the box is 1.5. And we have plus 2 times the acceleration of minus 4.24 times the displacement, which we want to calculate. Then we have to solve this equation for the displacement. And it goes as follows. 2 times 4.24 times the displacement is 1.5 squared. Then 8.48 times the displacement is 1.5 squared, so that the displacement is 1.5 squared divided by 8.48, which is approximately 0.265 meters. So this is how far the box travels before coming to rest.